I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology in the subject of Mathematical Methods of Physics 2 with the course code PHY 222. We are at the lecture number 11 and the topic is second order linear equation. These type of equations have got a lot of applications in physics and other areas of science. Because of their importance in applications, we will in detail consider that how to solve these equations. So in today's lecture, I will first introduce to you the linear second order equations, and then I will show you that how we can solve them. So let's begin and see the first and simpler form of the second order linear equation. It is actually a differential equation, which means it contains derivatives. So generally it is of this form. So where a2, a1 and a0 are some constants. If we analyze this equation term by term, so if you look at the second term, it is a second order derivative, that is d square by dx square of a variable y, which is a function of x, and it is multiplied with a constant a2, some unknown constant. And in the second term, then we have the first order derivative, that is dy by dx, and it is multiplied with another constant, an unknown constant a1, and the last term is not having any derivative, but it still has a variable y multiplied with another constant, third constant a0, and this is equal to 0. In this form, it is kind of simplest form of the second order linear equation. We will see in future lectures that it is possible that on the right hand side we don't have 0 and we get some function of x, and then the method of solution is a little bit difficult as compared to this equation. But let's at the moment concentrate on such equations and see that how we can solve them. Another thing is that about this equation, that it is a homogeneous equation because every term of it contains y or its derivative. So this equation is called homogeneous as every term contains either y or its derivative, as you can see over here. So it's also a homogeneous equation, but it is a second order and linear equation. So here by linear we mean that the power of y is not greater than 1. You see in first term, although there is a second derivative involved here, but the power of y is still 1. And in the second term, although there is a first derivative involved, but power of y is 1. And similarly in third term we have power of y is equal to 1. So in all of these terms the power of y is not greater than 1, so therefore it is a linear, homogeneous and second order differential equation. Such equations have got a lot of applications in physics, especially in physics. We will see in a moment. I will give you examples of it, but first let's try to solve this equation generally. So example of this equation, in order to just show you that how we can solve them, is this is an example where you can see the y is with a double derivative, and in this case you will see a2 is equal to 1, and then 5y prime means that this is the first derivative, so a1 is equal to 5, and then 4y naught, then a naught is equal to 4. So now we can try to solve it for y, and once we solve this equation, so from this we will learn the general method for solving this type of equations. So first of all, to solve this equation, to attempt the solution, we will change notation and put this equation in a different notation. For this we will write dy that is the derivative of y with respect to x, is equal to y prime. So this first derivative involved in the second term, y prime, we will write it dy, and there is a very good reason for it to adopt to this convention, and the reason is that we want to turn our this second order linear equation into an algebraic equation, which will be then easy to solve. So this is the reason. So you will see in a moment that how we turn with this notation, with the use of this notation, our second order linear differential equation into an algebraic equation. Okay, so as we are using a notation y prime is equal to dy, so we will also have to change the notation for y double prime, that is for the second derivative, and this as you can see easily equal to d square y. You can easily see from here, if y prime is equal to dy, then y double prime, or the second derivative, will be equal to d square y. So with this change of notation, our equation will become an algebraic equation, and the expressions involving d are called then differential operators. So these are all the differential operators. So this is a differential operator, and this as well as a differential operator. So whenever we change this notation, then we call these expressions as a differential operators, and using these differential operators, now our second order linear differential equation becomes of this form. So you see now it is d square y plus 5dy plus 4y is equal to 0, which just looks like an algebraic expression, and we can solve this expression very easily. Even at the school level, you have learned that how to solve these equations. So this d does not appear as a derivative, but it appears like some variable where we have taken square of it, or and then d linear of it, and then we can solve it just like a quadratic equation. So to make it more simple, we take the y common, so we are left with d square 5d plus 4 is equal to 0. So putting this equation into this form, and now you can easily guess that to solve this equation we can also use the factorization method. So we will factorize this equation to get factors, and it's very easy to factorize the equation and get two factors, that is d plus 1 and d plus 4 into y is equal to 0. And this is or this can also be written as d plus 4 plus d plus, the order does not matter, so either we can have d plus 1 or d plus 4, both of them are equally good, and this is equal to, because of the factorization you can easily check, this is equal to d square plus 5d plus 4. So after factorizing, now we know that we got two factors, and we will solve for each of factor independently. So we choose to solve first, for example, for d plus 4 or plus d plus 1. Since the equation was equal to 0, so therefore after factorizing the left hand side, we put that equal to 0. So this is actually the equation we started with. So it was the second order linear differential equation, which now has been transformed with the use of convenient notation and factorization into this form, or the other way around, just changing the order. So we first solve the simpler equation, which is this one. Since there is a multiplication involved, there are two factors over here, so d plus 1 and d plus 4 into y is equal to 0. So either d plus 1 is 0 or d plus 4y is equal to 0. So we take this simpler equation and solve it. I mean this one, that is d plus 4 into y is equal to 0, and we can also choose to solve d plus 1 y is equal to 0 to both of them. So we will first solve this, and then second we will solve this simple equation. So these are separable equations with the solution y is equal to c1 into e raised to power minus 4x, and y is equal to c2 e raised to power minus x. Now you can easily solve these two equations. D plus 4 into y is equal to 0. It's separable equation, so you can separate the variables, that is take that onto the other side and then solve for it, and you will see that what you will get is c1 into e raised to power minus 4x, and this is the another solution just got from the same method. So these are the two independent solutions, but we can combine them, combine these solutions to get the general solution. So now if d plus 4y is equal to 0, then we know that one of the if this one of the solution is equal to 0, then we can just put it into this algebraic form over here, and so any solution of d plus 4y is also a solution of this. So so if this if we solve this equation, which we have done here, this one, so this, if this is the solution of this equation, and we know that d plus 1 d plus 4 is equal to 0, so it means that the any solution of this equation is also a solution of this equation, as I have written over here. So any solution of d plus 4 y is equal to 0 is also a solution of this equation, which means that the general solution of d plus 4 d plus y is equal to 0 shall be of this form, that we can add these two, linearly add these two solutions, because it's a linear thing, so we can add them, the first solution and the second solution, and now from this way we have got the solution of the second order linear differential equation. And there is another interesting point to make over here, that this represents the structure of the vector space, because in this solution you can see that these two e raised to power minus 4x and e raised to power minus x are the bases, or you can say unit vectors, so to say. You can identify them as unit vectors. So these are the bases, and in this basis we can have a lot of solutions differing with the different values of c1 and c2. So it constitutes a full vector space with these two bases. So what I wanted to emphasize is that with these two bases, that is e raised to power minus 4x and e raised to power minus x, we have a complete vector space structure for the second order linear differential equations. So such type of equations are called auxiliary or characteristics equation, this one, d square plus 5d plus 4, and we were able to solve it algebraically and got its roots, that is minus 4 minus 1. So these solutions we got, e raised to power minus 4x and e raised to power minus x, was actually equivalent to the auxiliary or characteristics equation roots. So we actually have transformed the second order linear differential equation into the algebraic form, as you can see over here, and now this algebraic equation has roots minus 4 minus 1. So therefore the general solution, if we want to write even more general solution, where where we have instead of these constants over here some other constants, and in case a is not equal to b, then this is the most general solution you can see over here, because these a and b are just now the roots, so we can just put it here a and b form, and this is the most general solution we have got. So from this first part of the lecture, you have seen that when we have a second order differential linear differential equation with the right hand side equal to 0, then we can transform it into an algebraic expression having differential operators, and then just solve it by factorization or any other suitable method, and get the roots, and these roots correspond to the vector space structure, and then we have the solution, the general solution of this form over here. Okay. So here an interesting question arises about this values of a and b. So as you can guess that we have two constants a and b, and then there are three types of roots that we can have. For example, we can have real and unequal roots, which we have already treated now, because in the previous case the roots were -1 and -4, which were equal and unequal and real. But we can also have real and equal roots. What happens, I mean, when a is equal to b, that is the roots, in this case a was not equal to b, because which we have already treated, because we had -1 and -4 over here. But there is another possibility as well, that we have real and equal roots, and there is a third possibility as well, that when our roots are complex and conjugate to each other. So since we have already treated the first case, so now I am going to show you that in second case how we can solve still the second order linear differential equation in case of real and equal roots, and similarly for the complex conjugate case. So in second type, when we have real and equal roots, so our equation, this auxiliary equation or the characteristic equation, gets into this form, that is d minus a into d minus a, because a is equal to b now, so we can replace over here b with a, and this is now of this form. Now the problem is that once we have found one solution, because it must have two solutions, but once we have found the one solution, we can only find one solution over here with the method we have already learned. So to find out the second solution, we have to do something different. So for second solution, then we have to use this substitution. For example, we can call d minus a into y is equal to u. Let's introduce this new variable u, which is equal to d minus a into y, and then our this differential equation, auxiliary equation, will be of this form, because we can put for d minus a into y is equal to u is equal to 0. And now we have to solve this equation. We have to solve this equation to get the second solution. So it has the solution of this form, u is equal to a into e raised to power ax. So this is our second solution. So we got the first solution as explained in the previous example, and the second solution, after the second solution, the general solution will be this is the second solution, that is d minus into y is equal to a into e raised to power x, or y prime, if you put the values for d, minus ay into a raised to power a into e raised to power x. So the general solution is then for it is integrating it into this form, e raised to power minus x into e raised to power x, or ax plus b. So the general solution at the end we get is a plus ax plus b, and this y is because we had the previously one solution, a into e raised to power x. So the second solution is actually coming with ax plus b. So this is the complete general solution when we have two roots which are equal and real. Okay, now we move towards the third case, when we have roots which are complex even. Then the solution would be of this form. If you try again, the most general solution will be of a into, there could be many different ways to write the solution for the complex conjugate roots, but this is the form we have obtained. We can see if we solve that equation with complex roots, we will get alpha, where alpha and beta are the roots, and this will be the form of the equation we could have, or we can put it in a slightly different form, that is taking out the e raised to power alpha x. So, after discussing in the second part of the lecture the types of the solutions, you have seen that we could have three types of the solutions: real, equal, and real and unequal, and then complex. And we have solutions, most general solutions for all of them. Now, it will be interesting to see that how we can solve some equation of this type with the method we have already learned. So let's say this is some equation, and now you can see this is of the form we have discussed, that is y double prime minus 6 y prime minus 9 y is equal to 0. So it is second order homogeneous linear differential equation, and we can put this equation into auxiliary or characteristics type algebraic equation. This one, the first one, equal to 0, and then we just factorize it, d minus 3 into d minus 3, since we got this case when both of the roots are equal. So what next, we know that the solution for this is ax into b is for 3x, since we know that this is the root is a is equal to 3, and by this way we got the most general solution with two undetermined constants a and b. And these are the references, and at the end I would like to summarize for you what we have learned today. So in today's lecture we have seen that how to solve the second order linear differential equation. By second order we mean that we have a second derivative involved here, and we have learned that we can put such equations into the algebraic form by having an auxiliary or characteristic type equation involving the differential operators, and then we can factorize them or get the factors and get the most general solution. But when we factorize them, we could have three possibilities, that is real and having unequal roots, because it's an auxiliary or characteristics equation, so it has roots, or real and equal roots and complex roots. In all these three cases we got the most general solutions. So once we know the equation, we can just transform it into algebraic expression and then solve it in the simple way. We have also learned that such type of equations has got vector space structure of the solution of these constants as being the basis constituting a vector space. With this, I thank you all.